Hey geometry, let's take what we learned yesterday in lesson 26 about sine, cosine, and tangent and just take it one step further, dealing mainly with sine and cosine and how they relate back and forth to each other. For example 1, if alpha and beta are the measurements of complementary angles, then we are going to show that sine of alpha equals cosine of beta. In a right triangle ABC, the measurement of acute angle A is denoted by alpha, and the measurement of acute angle B is denoted by beta. Pause. Remember, we're dealing with right triangles where the other two angles are acute. This will never work with an angle greater than 90 degrees, only with angles less than 90 degrees. Continuing on. Determine the following values in the table. So we have sine alpha equals opposite over hypotenuse, which is A over C. Sine beta equals opposite over hypotenuse, which is B over C. Cosine alpha equals adjacent over hypotenuse, which is B over C. And cosine beta equals adjacent over hypotenuse, which is A over C. What can you conclude from this result? Well, if you just look at your answers, you can conclude that sine alpha is the same as cosine beta, A over C, A over C, and sine beta is the same as cosine alpha, B over C, B over C. Yep. Okay, since the ratios for sine alpha and cosine beta are the same, then sine alpha equals cosine beta, and the ratios for cosine alpha and sine beta are the same, so cosine alpha equals sine beta. Remember, they're just ratios, so the sine of an angle, is equal to the cosine of its complementary angle. Remember, complementary angles are two angles that when you add them together you get 90 degrees. Complementary angle. So let's practice that a little bit. Consider the right triangle ABC so that angle C is the right angle, and the degree measure of A and B are alpha and beta respectively. So the degree measures of angle A and angle B are alpha and beta respectively. So what is alpha plus beta? Well, we know that if angle C is a right angle, and this is, angle C is 90 degrees, and we learned a long time ago that angle C plus alpha plus beta equals 180, we can conclude that alpha plus beta equals 90 degrees. Use trigonometric ratios to describe BC over AB in two different ways. Well, first let's look at sine of angle A. That's going to be opposite over hypotenuse. And then cosine of angle B is adjacent over hypotenuse, BC over AB. They're the same. So we can use the trigonometric ratios to describe AC over, we already did that. Okay. What can you conclude about sine alpha and cosine beta? We can conclude that they are, in fact, equal. Okay? You can go back and they're both AC over AB. What can you conclude about cosine alpha and sine beta? Well, they are also equal. Okay, pretty cool. Okay, next part, let's take it a little bit further. Find values for theta that make each statement true. So remember, alpha plus beta is 90 degrees. So cosine alpha is equal to sine beta, and sine alpha is equal to cosine beta. Okay, so if we have 25 degrees here, we can say that the complementary angle with 25 is 65. So theta is 65 degrees. To make that statement true, theta and 25 have to be complementary, right? Same here, 80 and theta have to be complementary. So we know that 90 minus 80 is 10, so theta is 10 degrees. Pretty cool, huh? How about this last one? Sine theta equals cosine theta plus 10. I don't know, some of you guys can probably do some mental math for this one, but I'm just going back to the basics. Theta plus 10 has to be 90 degrees. So collect like terms, subtract 10 from both sides. Theta is 40 degrees. That's all I can do. How about sine theta minus 45 and cosine theta? Again, they should be complementary, so I should be able to add them together to get 90 degrees. I have 2 theta minus 45 equals 90. 2 theta equals, add 45 to both sides, I get 135. Therefore, theta equals, half of that is 67.5 degrees. Cool. For what angle measurement must sine and cosine have the same value? Explain how you know. If I give you these are the same, there's only one value that they can be. If we said they were both x, you would say 90 plus x equals 180. So 2x, subtract 90 from both sides, x equals 45 degrees. It's only valid for 45 degrees. So sine of 45 equals cosine of 45. And the other way around. Cosine of, I mean, you could flip it, but you just have the same thing. Awesome. Example 2. Okay, things will get just a tad bit more complicated. So if you think you're just going to coast through, push stop, and think you got the whole lesson under your belt, you're wrong. Keep watching. Okay? We're going to begin looking at special angles associated with sine and cosine, starting with the measurement of 0 and 90. Okay, this will be pretty awesome because it's going to lead to things like the unit circle, which you're going to see in Algebra 2. Okay, so there are values for sine and cosine commonly known for certain angle measurements. 2 of them are when theta equals 0 degrees and when theta equals 90 degrees. Okay, those are very important measurements. Okay, give theta there. So we're measuring that angle. So let's pretend that C, which is your hypotenuse, is a fixed measurement. C always equals 1, and this is the little c right there, the measure of the hypotenuse. So it's a fixed length of 1. Okay, it's almost like we have a circle. Okay, that should be right through the middle, and C is our radius. And the radius is 1. So what happens to the value of the sine ratio as theta approaches 0? Let me write that down. So what happens to the value of the sine ratio as theta approaches 0 degrees? Okay, consider what is happening to the opposite side A, because sine is opposite over hypotenuse. Okay, so I've got this radius of my circle right here, and I'm going to bring it down to make theta approach 0. So this stick, I'm angling it down to make that theta approach 0. Now I have to erase all that stuff. Alrighty. So, as theta gets closer to 0, sine of theta equals a over 1. A is going to get smaller and smaller and smaller. This is the measurement of this side right here. A is going to get smaller and smaller and smaller and smaller and smaller. So A approaches 0. Therefore, sine theta also approaches 0. Okay, so next, what happens to the value of the cosine ratio as theta approaches 0 degrees? Okay, let's look at what's happening to the adjacent side, okay, because cosine is adjacent over hypotenuse. So, as theta approaches 0, as we bring our angle down, B increases, approaches 1. Okay, let's look at it. As we close this angle, let's highlight it like we did before. As we close this angle and bring theta closer to 0, B is actually going to get longer and longer and longer and longer and approach the value of 1. And since we know that, cosine theta equals adjacent over hypotenuse, B is approaching 1. Therefore, cosine of theta approaches 1. As theta approaches 0. Cool? Awesome. Let's look at something else. All right, what happens to the value of the sine ratio as theta approaches 90 degrees? Okay, 90 degrees would be up here. So our angle is getting bigger and bigger and bigger. So what happens to the value of the sine ratio as theta approaches 90 degrees? Let's just consider what's happening to the opposite side, A again. Because as you remember, sine theta equals opposite over hypotenuse. So okay, here's our side. As the angle gets bigger and bigger and bigger and approaches 90 degrees, the side A is going to get bigger and bigger and bigger and finally end up at the value 1. So as theta approaches 90 degrees, the value of A approaches 1. So sine of theta would approach 1 over 1, or just plain old 1. And guess what we're going to do next? So what happens to the value of the cosine ratio as theta approaches 90 degrees? So we have to consider what is happening to the adjacent side, because cosine is adjacent over hypotenuse. Consider what's happening to the adjacent side B. So as we move this side and theta approaches 90 degrees, what is happening to B? Well, B is going to get smaller and smaller and smaller and smaller and approach 0. So as theta approaches 90 degrees, B approaches 0, which means that cosine, as theta approaches 90 degrees, B approaches 0, and cosine theta approaches 0. Okay? Big old bummer. And remember, hold on, I wanted to write this down because there are no right triangles with an acute angle of 0 degrees or of 90 degrees, because you need 3 angles in a triangle. In the above experiment, we are really just defining. We're making a rule or a definition. We are really just defining. That's awful. Sorry. Much better. We're really just defining that sine of 0 equals 0 and cosine of 0 equals 1. That's it. Pretty cool. I forgot to add that we're also defining that sine of 90 degrees equals 1 and cosine of 90 degrees equals 0. We have to do all 4 of them, okay? Okay, now let's move on to example 3. There are certain special angles where it's possible to give the exact value of sine and cosine. The exact value means there's no decimals, you're not rounding, there's probably radicals and whole numbers. These are the angles that measure 0, 30, 45, 60, and 90. We talked a little bit a few lessons ago about the 45, 90 degree triangle and the 30, 60, 90 degree triangle. They're very important, and you may end up memorizing some of the sine and cosine values. Okay. Where were we? You should memorize the sine and cosine of these angles with a quick recall, just as you did your arithmetic facts. Learn the following sine and cosine values of key angle measurements. We focus on an easy way to remember the entries in the table. What do you notice about the table values? If you look at sine and cosine, the hypotenuses, they're just hypotenuses, I don't know, are all 2. With the 45, they're square root of 2 over 2. With the 30 and the 60, they flip back and forth between sine and cosine. I don't know. Let's see what they say. This is easily explained. Let's see. This is easily explained because the pairs 0 and 90, 30 and 60, and 45 and 45 are all measures of complementary angles. For instance, sine of 30 equals cosine of 60, so that's why they flip back and forth. The sequence 0, half, square root of 2 over 2, and square root of 3 over 2 may be easier to remember than, or as the sequence 0, 1, 2, 3, 4 is all square root of 2, is all over 2, because this one right here simplifies to 2 over 2 or 1. I think this 1 is supposed to be next to the square root of 3 over 2. 0, 1 half, square root of 2 over 2, square root of 3 over 2, and 1. So it may be easier to remember this sequence than this one. Oh, because this right here is also just simplifies to 1 over 2. Okay, I'd never seen this before. It's pretty cool. It might help me memorize it, possibly. Could be cool. All right. Triangle ABC is equilateral, which means all of the sides of the triangle are equal in measure. Okay, they all have a side length of 2. D is the midpoint of side AC. Label all side lengths and angle measures for angle ABD. So ABD, I'm going to draw this straight down. Equilateral are also equiangular. They're all 60 degrees in measure. So here we have 60 degrees. Here we have 90 degrees, which means up here we have 30 degrees. Down here I have a side length of 1. And let's see, I can use Pythagorean theorem to figure out the other side length. Or I can use the 30, 60, 90 triangle. So this would be square root of 3. Cool? I'm going to draw this way. It might help some of us see it. This would be 60, 30, 2, 1 and the square root of 3. Cool. So sine of 30 equals, so is opposite over hypotenuse, 1 over the square root of 3, or square root of 3 over 3. And then cosine of 60 is adjacent over hypotenuse, ca. Oh goodness, scrap that. Let's try that again. It's sort of fun when you guys see me make mistakes, I think. Let's hope. Sine is opposite over hypotenuse. So, ca. So opposite is 1, hypotenuse is 2. Cosine is adjacent over hypotenuse. Oh goodness. 3 over 2. So just like the pattern that we learned, this is like square root of 1 over 2, comma, square root of 3 over 2. Sort of fun. I did forget to do sine, so I have to do, so I didn't do all 4. Cosine of 30, ca is adjacent over hypotenuse. Cosine of 30, adjacent over hypotenuse, square root of 3 over 2, and then sine of 60. I didn't read the instructions very well. Opposite over hypotenuse, square root of 3 over 2. Cosine 60, adjacent over, I didn't do that one right. You guys are probably giggling to yourselves right now. Cosine is adjacent over hypotenuse, so adjacent over hypotenuse is 1/2. Because these should be the same, duh, and these should be the same. Phew. Draw an isosceles right triangle with leg lengths of 1. What are the measures of the acute angles on the triangle? So if this is 90, this is going to be 45, and this is going to be 45. That'll be 1, and if I use the Pythagorean theorem, that will give me square root of 2 on that side. Use your triangle to determine sine and cosine of the acute angles. So sine of 45 and cosine of 45. Doesn't matter which angle we grab. Hypotenuse is right here. So we're going to do sine, which is opposite over hypotenuse, and cosine, which is adjacent over hypotenuse. So sine of 45 is opposite over hypotenuse, and cosine of 45 is adjacent over hypotenuse. Cool. Okay, here's another awesome little table to help you with the ratios. 30, 60, 90 gives us side length ratios of 1, 2, and the square root of 3. 45, 45, 90-degree triangles gives a side ratio of 1, 1, square root of 2. Okay, this is how I originally memorized it a little while ago, because it works with everything, but if you've got these triangles in your mind, you'll be good to go. Okay, 2 more exercises, and then we're done. Find the missing side lengths in the triangle. This is sort of like the meat and the potatoes of the lesson. This is why we did it. We're trying to find A and B, and we can use sine and cosine to do that. So what I usually do, first we have to know the hypotenuse, so I just drew an angle there. And now let's start with sine of 30. Opposite over hypotenuse. So sine of 30 equals opposite over hypotenuse. If you compare that to the table that in the previous slide, sine of 30, your ratio is, your ratio for sine of 30 is 1/2 for that basic triangle. So we can just take this and solve it. 3 equals 2a. A equals 3/2. Okay, try that with the next one. Cosine 30 equals adjacent over hypotenuse. So b over 3. Okay, compare that to the table on the previous slide. And our ratio for cosine 30 is square root of 3 over 2. I didn't leave that in very good places, did I? So I have 3 square roots of 3 equals 2b. Divide both sides by 2. This is a 3. 3 square roots of 3. So cross multiply. 3 square roots of 3 equals 2b. Divide both sides by 2. b equals 3 square roots of 3 over 2. Works great. And they're exact answers. They're not estimates. Okay, one more. Cosine of 30 equals adjacent over hypotenuse, 3 over c. And if you look at that previous chart, that gives me the ratio of square root of 3 over 2. Cross multiply. Divide both sides by the square root of 3. C equals 6 over the square root of 3, which simplifies to 6 square roots of 3 over 3, or 2 square roots of 3. Oh, I did it again. Rationalized right there. And then sine of 30 is opposite over hypotenuse. A over c. We now know what c is, so I'm going to write that in. 2 square roots of 3. Look at that previous slide, and that compares to 1/2. Cross multiply. 2a equals 2 square roots of 3. Divide both sides by 2. A equals the square root of 3. Sweet. You did it. Good job. See you tomorrow.